So hello everyone. I'm going to talk, as Darius said, about this Espedalen complex in Norway and its nickel copper sulfide mineralization. And towards the end, try to talk a little bit about the use of sulfides as indicator minerals that we learned a bit from here and other places, just to connect. Just to give you a broad context, we are traveling now to the northern part of the world. So we will be in central Norway, within the Caledonides in Norway. So this is a bunch of allochthonous blocks within Norway. And a special focus for us is this, what we call Jotun complex. Basically, 1.5, 1.7 million year old rocks on the top. A bunch of anorthosites being like, in this northern portion being really general. But we're focusing on this particular one here, which is called the Espedalen complex. It's basically a 8 kilometer per 6 kilometer allochthonous block. So this thing is not in place. It's been thrusted within the Caledonides. It's 1.5 billion years. We have a northern section of some Charnokites and Jontunites, so I'm not going to talk today. I'm mostly going to concentrate on the central portion, which is these anorthosites to gabbronorite rocks with these ultramafic plugs. Why are we interested in those? All these squares are areas that were explored or are under exploration now. With all the red dots are drillings. So two main resources to date where they're being explored is this Dalen in the middle of the complex. So this ultramafic rocks, neck texture, pretty nice textures, but more disseminated to neck texture sulfides, and some other that is called Sturmira. And these are the two complicated names that I'm going to talk, I swear to God. And these are more massive sulfides, and they are in the contact with the complex and the more tectonic complex. So just a bit of the texture. So outcrop, it varies. In some areas it's pretty good, some areas not that well. But from the cores, we can see that this gabbronorite, sometimes reaching an anorthosite, gets pretty deformed. This happens in some corridors, so few meters, or in the terrain or in the field, you can walk for several hundreds of meters within completely deformed, no preserved textures. Whereas in some other places, you still manage to get their textures. And the textures are even more preserved when you are in these ultramafic portions within the complex, although they are smaller. The mineralization itself, we have divided into primary sulfides, which are dominantly hosted by the ultramafic rocks. We rarely find these pristine textures of Indian anorthosites, and they are mainly disseminated sulfides. So net textures, you rarely find some massive. Deformed sulfides, which then are in shear zones, and these tend to be relatively massive. The textures are gone. You've normally find this segregation, some bands of pentlandite and pyrrhotite being alternated with each other. And these you do find in gabbronorites, but they tend to be within 1 to 2 meter shear zones, like pretty flat line structures where you do find this more brecciated to massive sulfides within them, and pretty pentlandite pyrrhotite rich ores. And in both occurrences, you do have what we call like this remobilized sulfides. So these veinlets of sulfides, the cross-cut, both of them. So these are what we interpret as some like late remobilization. You do find them in different places, and they're less of an important for today. In terms of the geochemistry, this is just like the past and ongoing exploration assay that we put it together from them, including some more massive sulfides, net texture, or this brecciated, and this disseminated ores. And one thing that is nice is, although we do have this very different deformed and primary textures, in terms of composition, these will be open and closed symbols. They're not that really different. So they do have a similar composition from them, which is pretty distinct from this lower tenors for these remobilized sulfides that you do find. So we calculated the nickel tenors, the tenors for nickel and copper. So basically the amount of metals in the sulfides only. And we see, although I haven't labeled the targets individually, it will be too confusing. We do have differences, but these are not related to, oh, these are primary or deformed or so on. They pretty much, you do have primary and deformed sulfides pretty much all over. And tenors that go from 6 to 7% nickel up to in the primary and much lower in the remobilized. One thing that was pretty remarkable is that they are pretty much PGE depleted. So for instance, palladium, even the more massive ores, they pretty rarely reach and almost never exceed 0.1 ppm, so they're very low in PGE. So just a common little approach for how do we think these things are PGE depleted. One problem that we have encountered so far, this is an ongoing work, but we have no proxy for an initial magma, so we have no chilled margins to work on. So we basically did some minerochemistry, estimated sort of a high magnesium parental melt for the stuff especially hosted within this ultramafic cumulates. So we assume something sort of like 10 ppb, sorry, of palladium, 50 ppm copper. And as long as segregate sulfide liquid, you normally use, it's not my ideas, but palladium and copper. Palladium increases much more rapidly than copper. And you imagine your sulfides should plot within this line, but they plot way below. So basically you should be dealing with something that should be here rather than up there. The way of doing that is your parental magma actually should be depleted in PGE, and then you keep segregating, interacting your magma with higher R factors to generate the stuff. Just for sake of comparison here, so we call this like similar to the Voss's-based models that have been proposed, like a two-stage segregation, just a compositional field for reference in there. One thing that we also find that it's interesting is that in general, when sulfide liquid segregate crystallizing again, established concept, MSS first crystallizes, and then this copper fractionated liquid will keep going on. But iridium is compatible to MSS, whereas palladium is incompatible. As a direct result, when you have like MSS cumulate ores, they have low palladium iridium ratios. When you have ISS or more fractionated ores, they have high palladium iridium ratios. And what we do see at Espedalen is basically we only have this palladium, low palladium iridium ratios with this pyrrhotite and pentlandite dominated ores. Nothing has been identified so far that has this more copper-rich signature in the complex. It may be something normal, I don't know, maybe something that is missing in the system yet. There's something I don't have any answer for that. A little schematic model for that, how to put that together, and I have no attachment to shapes of the chamber or anything. The amount of information at this stage is not extensive, so it's more of, we believe that you segregated some early sulfides at the beginning. Just a parenthesis, we published a paper a while ago, and we got in mail, so this is Mike Lesher's comments, not mine. So an alternative hypothesis could be that we're dealing with a pyroxenitic mantle relative to a more peridotitic mantle. And one of the reasons for that is that you have like the southern portion of Norway, the southern eastern portion of Norway, all the deposits that we have, like these occurrences, they are PGE depleted. So that's, but that's something that is sort of an idea that will be worked on. We think there are several processes for forming this little complex with some MSS segregation and the further deformation that's localized in this more massive ores in the shear zones. There is a lot of percolation of fluid, so there's quite a lot of pyrite that forms on these more deformed ores. We have analyzed those that are secondary replacement pyrites. So there is some local remobilization after. But then we started thinking, okay, how could we potentially expand what we are seeing here and find in other areas? In other extensions of this anorthositic complex, we do have exposure, but in other portions, sort of more the north and the LDU north portions, they are undercover, so you have a lot of till, a lot of glacial. So we started thinking, okay, could we try thinking of something for indicator minerals? The concept is basically, if you have some sort of occurrence, but a cover, can you recover something from the cover and without any sort of textural idea, so just individual sulfide grains, look at the composition and say, oh, this is interesting, this is not interesting. There's a pretty nice work by Charlie Duran on that. That was in 2019 that tried to do that in Canada, so I really recommend checking on that. And for sulfides, there's been a lot of discriminant diagrams that have been proposed. We could criticize or not those, but it's sort of what's been on. I've criticized them as well as proposed. But the idea is like we can roughly separate magmatic from hydrothermal compositions. I'm not going into any detail. We can talk about that at any stage if anyone is interested. From the magmatic, the two main differences should be nickel, copper, and PGE dominated. If we find a PGE dominated signature, you're fine. So I mean, there's no much more you could go from there. But the main question is like, can you differentiate in terms of composition, low tenor nickel copper and high tenor nickel copper? Basically, because you'll be pretty happy if you can get into that. So is there any sort of proxy for barren sulfides? And I think one of the main problems with discriminant diagrams and indicator minerals is that people are trying to think as Lord of the Rings fashion, some one to rule them all. Like I want to have one diagram that I'll just plot and I'll see, oh, this is pretty good, this is not good. But actually, if you don't go through the different steps, I think it's hard. Marie has the same approach for apatite, which I think is super nice. So I really think you should use several different discriminant diagrams to understand what's going on. This is just a thought that we had. So for instance, I'm going to use selenium and pentlandite, but there are other proxies as well that one can use. Each point is one whole rock analysis. And so we compiled from literature the tenor that will be from that occurrence and the average sulfide composition from that place. We see that the data from Espedalen plots also within that. And we see that there seems to be a sort of a correlation to that. And the thing is, like, if you the problem with sulfides that I think you should try getting elements that are not really remobilized by post-cumulus effects, because otherwise it's way too much overprinting information in their composition. So just the detail on Espedalen, we do see that higher tenors tend to have like higher selenium compositions. We can discuss why on that, but it's just a sort of a thought on how can we try to use those sort of proxies. Yeah, I hope I haven't extended much my time. And thanks, that's just a nice bromide.
I want to ask the tectonics of these deposits, are they related or related to subduction?
Yeah, we think yes. The problem, this particular little guy, it's hard as an lactanose block, but the general, when you look at more generally, we think they are related to this long convergence setting from the Svekon that would lead to this Svekon region, so from 1.5 to 1.0, a series of accretionary margins that will lead to that. So that is one of the current idea has been on work, but that is what we believe they are part of. Yeah.
Questions. Thank you.
Thank you.
That's the end of the session for today.